Welcome to the course on Introduction to Electrical Engineering. We will discuss today lecture 6, the topic Analysis of DC Circuits, part 4. The outline of today's presentation, we will start from introduction, then we will talk about the theorems, especially for superposition theorem, Thevenin theorem, Norton theorem and maximum power transform theorem. These theorems are used certainly for simplification of the circuit and solving the you can call it complex AC as well DC as well as AC circuits. Then we will follow the some you can call it numerical problem followed by the references. So, coming to the introduction of this today lecture, the number of electrical and electronic circuits can be solved using the Kirchhoff's current law and Kirchhoff's voltage law, node analysis and mesh analysis, which discussed in last few lectures. However, some electrical engineering applications, especially in electronics engineering, involve network with large number of components and needs some special technique for the circuit analysis, and various techniques are based on Kirchhoff's current law are used for the circuit analysis. And these main techniques or the theorems which we like to discuss today are typically like a superposition theorem, then Thevenin theorem, Norton theorem and maximum power theorem. Well, each of these techniques or theorem have strength aimed at solving particular types of circuit problems. Starting first algorithm or theorem, you can call it the superposition theorem. It has applications especially consisting the circuit with more than one energy units. As you can see here that we have a typically couple of batteries connected in series with the switch and typically the lamp load, because it is a kind of DC circuit. And well, this is the typically maybe a cases that you have a couple of sources followed by the load, and you have a depends on if you are having a AC current, a DC source. So, you will have a DC current and you have a AC source, then you will have a certainly the AC current like So, there are plenty of applications with the multiple sources, and nowadays day by day these sources are increasing. The typical example is today we have like a solar photovoltaic generation system, then wind energy generation system, we have a DG set also, and typically we have a local load, and as well as we have to keep a storage to take intermittency of renewable, especially the solar and photovoltaic. So, these kind of applications are increasing day by day, and we name these sources with the entire electrical system or circuit with these sources. Typically, we call it microgrid, or many definitions are there for, you can call it standalone system, or you call it distributed energy system, and they are coming very much in practice. If you look into an example, we have around 4.5 lakh telecom towers, and all majority of such systems certainly have a DG set. Because there may not be even a grid there, and you have a certainly other loads also other than your, and of course, we have energy storage like a battery there, and many towers now we have already the solar, and wherever the wind exists, we also connecting the wind. There may be grid, there may not be grid. Such applications are coming up great into the even today electrical network like. And you can just see the kind of another circuit which have a multiple sources. You can look into here that you have a wind generators, you have a fuel cell, that is another people are expecting. Supply from the fuel cell with through micro turbine directly from fuel cell, and we have a lot of power converters with the energy storage, maybe battery energy storage or some other storage also, with of course the power electronics control load, that you can control the load also, and many with the energy storage and power electronics interface with the grid also. So, you can take a typically you can call it power from the grid, or you can feed the extra power to the grid, or you can regulate the power flow into the grid in such network. So, there are plenty of such networks are now day by day increasing like of course, it was existing earlier also. So, coming to this with the basic principle that it helps superposition theorem especially help us to analyze this linear circuit with more than one independent sources, as we have seen in the diagram, and it is used to determine the value of variables like voltage across the resistance and current through the resistance, and it is applied by calculating the contribution of each independent sources separately, and the output of a circuit is determined by summing the individual responses of each individual sources, and the idea of superposition rests on the linearity property of the circuit. So, how we define the linearity? It is a property of an element describing the linear relationship between cause and effect. So, it is a combination of both homogeneity, especially scaling property and additive property. As you can see, the linearity can be defined as a part of homogeneity, superposition and additive properties. So, we can define like this linearity as a homogeneity. The homogeneity property requires that if the input, also called the excitation or the source, is multiplied by a constant, then the output, also called response, is also multiplied by the same constant. So, as you can see here that we have a, let us say x 1 x 2 and many input and output is y. So, we can say that if you multiply this by alpha input alpha alpha x 1 alpha x 2 and so on, then output will be alpha y. The typical example says a typical Ohm's law that V equal to I R, but if we multiplied it k on I R side, k I R will be equal to k V, because this Ohm's law is applied basically on the, you can call it linear electrical circuit like also. So, that is typical example of concept of linearity and homogeneity. Then coming to additive property of linearity, so it requires that the response to a sum of input is the sum of responses to each applied separately. So, the basic concept is, let us say we have a input x 1 a, x 1 x 2 a and so on, and output is y 1 a, and you have another typically set of input x 1 b, x 2 b, and output with that input is y b. Then if you add these two input x 1 a plus x 1 b and x 2 a plus x 2 b and so on, then output will be y a plus y b. So, that is virtually you can call it the additive property of this your network like or electrical circuit like also. Now, you can call it what is the this as an example as a linear typically additive property, the voltage current relationship of a resistor. If you take an example here in the circuit, that source is V s a DC and we have a linear circuit and output is the typically the load with where the current flowing I. So, we can call it, if you have a let us say the voltage source as a V 1, then you will have a output I 1 R, current flowing I 1 through this resistor, and another time we may have a like when current I 2 is flowing, that will be V 2 equal to I 2 R. Then we can apply that, if we apply current I 1 plus I 2 to the load, then it will be V will be equal to your I 1 plus I 2 into R, or it will be equal to I 1 R plus I 2 R, and that is equal to V 1 plus V 2. So, this is a kind of additive property of typically of this linear circuit, where we think the concept of applying the superposition theorem like So, after discussing this concept where we can apply the superposition, we have a statement of superposition theorem in any linear bilateral network containing two or more independent sources like voltage source or current sources or combination of voltage and current sources. The resultant current or voltage in any branch is the algebraic sum of the current or voltage caused by each independent sources acting alone, with all the other independent sources being replaced meanwhile their respective internal resistances. Well, the typical basic principle is like you see this circuit that we have a two sources V 1 and V 2, and this will be equivalent to that you apply the V 1 and you apply again V 2. This will be the sum of the responses of the both. So, superposition for two independent voltage sources, and now superposition two independent current sources, that you have a two current sources applied to a network like I 1 I 2, that will be equal to that when you apply the current source I 1 plus when you apply the current source I 2, that will be equivalent to that like. So, this is something concept of like a superposition theorem. We like to of course discuss in detail with the examples. So, what two things to remember keep in mind while applying this superposition theorem: to turn off a voltage source. So, it is replaced by an internal resistance or short circuit, an ideal wire. The voltage across the ideal wire will be exactly the 0 volt. Then you can just have a simple example here. When we have a typically a circuit, so we can a voltage source is there with the 0 voltage. So, it can be just represented as a current flowing through this like a short circuit if there is no internal resistance of this source. And then to turn off for a current source, to turn off a current source, it is replaced by an internal resistance or open circuit or an air gap. The current through the air gap is exactly 0 ampere. Typical example here that you have a 0 current, like typically in the source, then it will like it to be taken in the circuit as a like open circuit like also. So, well, the dependent sources need not to be zeroed, they remain the same as for every solution and may affect every solution. So, typical example here you have a dependent source like a with the 3 I, because current I is going to be from the 24 volt source. So, this need not to be replaced like also. but other two sources of course can be current source have to be like open circuit and voltage source have to be like a short circuited while you are doing one at a time for applying the superposition theorem like. So, now typically steps to apply the superposition theorem is step 1, retain one source at a time in the circuit and replace all other sources with their typically internal resistances, and step 2, determine the output current or voltage due to the single source acting alone using the techniques nodal or mesh analysis, and step 3, repeat step 1 and 2 for each of the other independent sources, and step 4, find the total contribution by adding algebraically all the contribution due to the independent sources. Typical example here, an example 1, find the current I 1 in the circuit shown here in the figure, where you have a two sources of 12 volt supply and 18 volt DC supply, where the two resistances 2K and 3K are shown here. So, first step is that we are second source of 18 volt, we are just short circuiting that because it does not have internal resistance. So, now we have a step 1 with the 12 volt source with the both the resistance in series, and we are finding a current, let us say we call it like a I 1 current. So, I 1 current will be like a minus 12 volt plus your both the resistance 2 kilo ohm plus 3 kilo ohm. So, current is minus 2.4 milliampere, and the second step is that when we short circuit the first source and we apply the second source, then we find out current I 2. So, this I 2 is 18 volt source is there. So, 18 volt divided by 5 kilo ohm in the same resistance of the circuit. So, this comes 3.6 milliampere. Now, we can find out the typically the I total I into the circuit, and with that we can say will be sum of I 1 plus I 2. So, I 1 is minus 2.4 and I 2 is plus 3.6. So, the net effect will be your with the proper polarity of 1.2 milliampere. So, that is typically how we apply the superposition theorem with the multiple your independent sources, voltage sources in the circuit. Now, coming to another example, by means of superposition theorem, calculate the current in the network shown here in the figure. So, we have here two voltage source, one of 10 volt and 20 volt, and we have three resistances. So, we have to typically find out these currents I 1, I 2, and typically I 1 plus I 2 in all, you can call it current in all three resistances like. So, again we go to with the typical example that first we take the first source and second source we short circuit. So, keeping the one source at a time, that is 10 volt first. So, total resistance of the circuit we can do the typically 1 ohm in series with the 18 and 2 ohm in parallel. That equivalent resistance comes with this calculation at equal to 2.8 ohm, and we can find out what will the current corresponding I 1 be. Here it is a 10 by 2.8, that is a 3.57 ampere, and I 2 be under this condition will be your typically the division of this current into. So, it will be 3.57 into 18 by typically 20, that is the current flowing into that. So, that will be minus 3.21 ampere. So, current I 2 be the negative due to the direction in which it has shown. So, either actually the current will be flowing in opposite direction, but sign convention that says current is negative. So, that is with the first source. Now, step 2 with the considering the second source of 20 volt in the circuit. So, total resistance here will be coming now, this 18 ohm resistance is in parallel 1 ohm with the addition of 2 ohm in series. So, it comes 2.947 ohm, and now we can find out what is I 2 C, that is 20 volt divided by this total resistance, so 2.95. So, that becomes 6.78 ampere, and I 1 C the current flowing into 1 ohm, that is of course, the current with the minus sign, that is 18 divided by 1 plus 18 into 6.78, and this becomes minus 6.42 ampere like. So, we know the current of course, in different branches by two sources, and now we can apply the superposition theorem to find out this I 1 current by the two cases. So, that will be equal to I 1 equal to I 1 B plus I 1 C, and that current is 3.57 minus 6.42, this current minus 2.85 ampere, and I 2 is I 2 B plus I 2 C, and this is equal to minus 3.21 plus 6.78. So, that becomes equal to 3.57 ampere, and if you take a current in 18 ohm resistance, that is I 1 plus I 2 as shown in the circuit notation, we can add both current. So, it is with the proper polarity minus 2.85 as we got it plus 3.57. So, this become current equal to 0.72 ampere in the middle branch of 18 ohm. So, coming to example 3, the compute the current in the 23 ohm resistor, extreme resistor of the figure by applying the superposition theorem, where we have a one voltage source, one current source, and typically the 4 resistance in the circuit. So, we like to take one source by one. So, first we take only voltage source, but in this condition the current source have to be made open circuited because it does not have any internal resistance like. So, taking this circuit, now we can find out the different currents here. So, we can find out the total equivalent resistance across the source will be like your 47 ohm in typically as a series resistance, followed by the 4 plus 23 27 ohm, and then this in parallel with addition of 27. So, total resistance comes 60.5 ohm. Now, we can find out the IT total current coming from the source, that is 200 volt divided by total resistance of 60.5, that is 3.31 ampere. This is the current IT coming from this voltage source. Now, we can find out the current going to be of typically I dash 23 ohm. So, that current will be divided into two parts. So, that will be, because this is 27 ohm divided by total resistance of 54 virtually into 3.31, and that will be equal to 1.65 ampere like. So, now step 2 is taking the current source only and taking a voltage source as a short circuit. So, in this case we can again find out the equivalent resistance on this side. So, that is typically 4 multiplication parallel of the 27 and 47 of this. So, it comes 21.15 ohm, and we can find out the typically the current now into the branch of this, that is we call it I double dash 23. So, it will become a part of this total resistance 21.15 divided by 21 point plus 23, because this current is divided into two parts into 20. So, it becomes current like equal to 9.58 ampere. So, the total current in the 23 ohm is sum of the two cases. I 23 ohm is I dash 23 ohm plus I double dash 23 ohm, that becomes sum of these two currents, that come 11.23 ampere like. Now, superposition theorem have some limitations. It cannot be applied for the cases. It does not work for the calculation of power, because power calculation is not a linear operation. And example is when current I 1 flows through resistor R, the power is P 1 equal to your R I 1 square. So, when current I 2 flows through resistance R, the power is P 2 equal to R I 2 square. So, if the current I 1 plus I 2 flows through the R, the power absorbed by P 3 will be R I 1 plus I 2 square, and this will be equal to R I 1 square plus R I 2 square plus 2 R I 1 I 2, that is not equal to P 1 plus P 2. So, that is the reason means superposition theorem cannot be applied for the power. It is only applicable for voltage and current relation in this linear circuit like. Thus, the power relation is non-linear. So, it cannot be applied for that. The another limitation is typically how we can find out this, just with an example this limitation. So, using superposition, power consumed by the individual sources in this network we can find out. So, power due to the one 12 volt source will be 12 watt, and power due to the second 12 volts also will be 12 watt. So, total power will be of superposition 24, but here superposition principle fails, hence the current flow through the resistor is 0, because 2 voltage will be just opposite. So, superposition cannot be applied for the power calculation. Here look like we took individual sources, then power consumed and current flowing were typically of having power 12 watt, but both battery are having equal voltage. So, there will not be any current flow and power in actual sense, no current flow and no power absorbed, but superposition theorem says that it will have a power dissipated in this 12 ohm resistance as 24. So, that is the reason this superposition theorem is not applicable here for the power relation like. So, another limitations of superposition theorem is the superposition theorem cannot be applied for the nonlinear circuit like consisting diode and transistors, which are nonlinear element, and with the simple circuit this is easy, but in a large circuit this method becomes a painful experience like. So, that is about the superposition theorem. Now, we come to the second theorem of today explanation, that is Thevenin theorem. This Thevenin has invented this theorem. So, it has been put on the name of the person like a Thevenin theorem, and this theorem is also application is it often occurs in practice that a particular element in a circuit is variable, usually called the load, while other elements are fixed. As a typical example, a household outlet terminal may be connected to different appliances constituting a variable load. and each time the variable element is changed, the entire circuit has to be analyzed all over again. To avoid this problem, Thevenin theorem provides a technique by which the fixed part of the circuit is replaced by an equivalent circuit, that we call it Thevenin equivalent circuit like. So, typical example is, let us say we have a supply system in home, and we have a separate several load on this. Typical example load may be your fan, as you have seen in figure, or maybe a like iron press, or it is a like a lighting system or light. So, electric wall socket acts as a load terminal, where variety of loads can be connected according to the user requirement, but internal circuit always remains the same. So, since the internal circuit is fixed, so repeated analysis of this circuit can be avoided by using the Thevenin theorem like. So, typical examples is here, that for applying here you have a circuit which have a voltage source and current source, and you have several resistances internally in this circuit, and then you are connecting this load and across the terminal A B. So, now this can be represented as equivalent to a Thevenin circuit, a equivalent voltage which you call it VTH with the polarity, and another series resistance RTH across the AB terminal. And then now you can put the different load. So, but this network, all this entire equivalent network which are shown very complicated in the dotted line, can be just represented as a voltage source with the series resistance. So, this we call it Thevenin equivalent circuit for dotted part of the circuit, and where VTH is the Thevenin equivalent voltage and RTH is the Thevenin equivalent resistance like. Well, the typical applications are like typically as a audio amplifier, where we have a Thevenin theorem applied there. So, we have a speaker with the different resistance, typically may be Z equal to 8 ohm, and on amplifier which is like a AC source, we have a internal impedance of it of 500 ohms. So, this is a quite complicated circuit of audio amplifier, but we can represent equivalent to a Thevenin voltage source and Thevenin equivalent source of this order like also. Well, it provides a mathematical technique for replacing a given network as a weaved from the two output terminal by a single voltage source with a series resistance or impedance, depends whether you are applying for AC circuit or DC circuit. And statement of this Thevenin theorem says that Thevenin theorem states that a linear two terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with a resistor RTH, where VTH is the open circuit voltage at the terminals and RTH is the input or equivalent resistance at the terminals when the independent sources are turned off. So, why are we using this Thevenin theorem? It simplifies the process of solving for unknown values of voltage and currents in a network by reducing the network to an equivalent series circuit connected to any pair of the network terminals. Well, it is especially useful in the circuit analysis of power or battery system and other interconnected resistive circuit, where it will have an effect of the adjoining part of the circuit like. So, main concern in the Thevenin theorem is to find Thevenin equivalent voltage and Thevenin equivalent resistance RTH. So, here the two circuits given here are said to be equivalent if they have a same voltage current relation at their terminal. The typical example here, if you have a original circuit which is quite involved linear two terminal circuit across the terminal A B, and you are connecting the load and you have a voltage across V and current I, that can be represented as equivalent to a Thevenin equivalent circuit with the voltage source VTH and the internal resistance RTH and current flowing into this same I, and you have a voltage across the load V. So, this is what we call it equivalent circuit, Thevenin equivalent circuit of this original circuit like. So, now we can say if the terminals A B are made open circuited by removing the load, no current flows, then the open circuit voltage across the terminal A B is equivalent to the voltage source that called VTH or Thevenin equivalent voltage also. So, that is how we have to find out the Thevenin equivalent voltage or Thevenin equivalent circuit voltage like. Thus, the VTH is the open circuit voltage across the terminal VAB by removing the load across the AB, across which we want to have a Thevenin equivalent circuit like. So, that is VTH equal to VOC. Now, coming to this R in or R Thevenin, the linear circuit with all independent sources set equal to 0. So, the input circuit, or we have to make the passive circuit virtually you can call it, the input resistance or equivalent resistance of the dead circuit at a terminal A B must be equal to RTH, because the two circuits are equivalent with a load disconnected terminal A B, open circuit and all the independent sources are turned off. So, thus the RTH is the input resistance at the terminals when the independent sources are turned off, and that RTH equal to R in of this linear circuit like. So, for finding the Thevenin equivalent circuit RTH, let us consider the two cases. Case 1, when the network has no dependent sources, so turn off all the independent sources, then RTH is the input resistance of the network looking between the terminal A and B. Case 2, when the network has a dependent sources, so method 1 is turn off all the independent source and apply the voltage source V 0 at the terminal A and B and determine the resulting current I 0, then RTH will be V 0 upon I 0. And method 2, the turn off all the independent sources and insert a current source I 0 at the terminal A B and find the terminal voltage V 0, then RTH will be V 0 upon I 0. Then step 2, determine Thevenin equivalent circuit and voltage, remove the load resistors RL and or component connected across the output terminal and determine the RTH by sorting all the voltage sources or by opening the circuiting all the current sources and calculating the circuit resistance, total resistance as seen from the open terminal across which you are finding the Thevenin equivalent, and determine the VTH by calculating the voltage between the open terminal A and B by usual circuit analysis methods, and find the current flowing through the load resistance after this Thevenin equivalent circuit. Now, coming with the typical example to find the Thevenin equivalent between terminal A and B in this circuit. I mean A and B, you can see the two terminals and you have a typically the current source as well as voltage source. So, but there is no dependent sources here. So, we have only independent source. So, first case is for RTH, remove all the independent sources, replace the voltage by a short circuit, voltage source as a short circuit. I mean this voltage source is shown short circuit and the current source is just shown as a open circuit. I mean like, so this circuit becomes, I mean in this manner, you can just see an example, and this circuit now we can replace it, I mean by keeping these two resistance parallel, I mean 20 ohm, by parallel resistance comes 10 ohm, and now this circuit is typically you can call it looks like a delta connected on this side or typically of or this side. So, you have to convert one equivalent to of this one side of delta, you have to connect typically, I mean this is star also you can connect into delta, and now you can see these two resistance are coming parallel and this is also coming in parallel and this is typically further parallel of these two. So, or you can even converting equivalent to delta also, that also will simplify. So, this will require typically an star delta, you have to think about which one make more simpler calculation. So, just after applying the star delta transformation of this network, you connect the typically star to delta here. So, this network simplified to simple parallel circuit, and this parallel circuit now you can find out that here 30, I mean this 30 here 30 ohm is parallel with the 10 ohm, in two cases that comes 10 ohm. So, now the circuits get simplified virtually into this manner, I mean like which simplified to 32 like a 15 ohm in parallel like, I mean also. So, well now coming to finding out the Thevenin voltage. Now, for finding out Thevenin voltage, what we have to do it here, I mean we have to typically of course, we have open circuit already those two terminals, and now convert this current source into a voltage source, and now this circuit modified into this fashion, because these two typically, I mean this is a net circuit. Now, we can find out what is the open circuit voltage coming across it after converting current source into the voltage source like. So, now for the loop 1, we can do loop analysis for this circuit to find out the voltage across A B. So, for considering the first loop, so we have a minus 30 volt current is entering here I 1 plus 50, typically the, I mean you can call it like a another 50 volt with the positive sign, because current entering in the positive voltage, plus typically the 30 ohm is the resistance coming in the path of this, and 10 typically for this 10 ohm is the minus 10 I 2. So, that becomes a relation, I mean simply because minus 2 equal to 3 I 1 minus I 2, and for loop 2 in second loop we have again the, we can write the equation typically here with the minus current is going to minus terminal. So, minus 50, and here also it is going to be minus, that is a minus 10 equal to 30, total resistance is 30 I 2 in the path minus 10 I 1 typically here, and this gives the relation 6 equal to minus I 1 plus 3 I 2, and solving these two equations we get the I1 equal to 0 and I2 equal to 2 ampere. Now, finding out typically here equivalent voltage. So, we can apply the voltage now to get this voltage between these two terminals. So, we have to get this voltage to this voltage. So, you can call it VAB will be equal to minus VAB this voltage minus tan I1, the current I1 flowing through this, plus 30 typically a 30 minus tan I2 this. So, now you will get the VAB equal to a 10 volt like from this circuit like also. Now, you can call it therefore, the VTH equal to VAB equal to 10 volt. So, now this whole we can represent it this 10 volt source and with the 10 ohm resistance. So, this becomes a equivalent Thevenin equivalent circuit of the total circuit like. The note is here for non-ideal independent sources, replace them by their internal resistance while deactivating the sources like. So, example is to find the Thevenin equivalent between the terminal A and B, and here we have a dependent source. This is dependent voltage source of this voltage. So, turn off all the independent sources and apply the voltage V 0 at the terminal of A B and then determine the resulting current. Then we can call it RTH will be V 0 upon I 0 like. So, that is typically from this circuit we have a like you can call it converting this 5 ampere current source replaced by open circuit. So, this we are making open circuit here, and then now we are keeping a here the 1 volt source here, and now we are finding typically you can call it the solving this circuit total circuit. So, from the loop equation we can find out in this loop that is minus 2 V x plus 2 I 1, that is I 1 current in this direction minus I 2 current in opposite direction. So, that is so it give a V x equal to I 1 minus I 2, and in the second loop by putting this minus 4 I 2 the typically equal to V x equal to I 1 minus I 2, and therefore, I 1 equal to minus 3 I 2, and from this you can have a typically second loop equation 4 I 2 plus 2 I 2 minus I 1 plus 6 I 2 I 3, that comes equal to 0. So, for loop 3 this is the loop 3, you have a 6 I 3 minus I 2 plus 2 I 3 plus 1 this voltage source. So, by solving that we get I 0 equal to I minus I 3 equal to 1 by 6 ampere, and therefore, Thevenin resistance will be equal to V 0 I 0 1 volt source we have taken divided by this current of 1 by 6. So, it comes like a 6 ohm. So, now we can say typically the Thevenin resistance is typically of your 6 ohm, and now we want to find out the Thevenin voltage open circuit voltage here. So, we have to find out VOC for reduced circuit in this figure. So, applying the mesh analysis we can find out typically I 1 here that is equal to 5 ampere, and for loop 2 in this loop we can say 4 I 2 minus I 1 plus 2 I 2 minus 2 I 3 plus 6 I 2 here that is equal to 0. So, it becomes like a just solving it becomes 12 I 2 minus 4 I 1 minus I 2 equal to 0. So, that is typically the second equation. Now, for the loop 3, that is loop 3, that is minus 2 V x equal plus the voltage drop here 2 into I 2 minus I 3, and that gives the relation V x equal to I 3 minus I 2, but for I 1 minus I 2 equal to V x. So, we can find out from solving these I 2 equal to 10 by 3 and V t h will be V o c, that is typically yours the voltage here, because there is no current here. So, you can call it 6 I 2 in the current flowing into this. So, that is I 2 is already 10 by 3. So, you can call it like it becomes like a 10 by 3 into 6. So, it becomes 20 volt. Now, your Thevenin equivalent becomes here of this circuit, it is a 20 volt and with the 6 ohm resistance. So, this complicated circuit modified to this Thevenin equivalent circuit like which have a dependent voltage source, we have a current source, and finally, simplified to this circuit like. So, now coming to the Norton theorem, that is the another theorem with the name of Norton who invented it. So, the statement of this Norton theorem is it states that a linear two terminal circuit can be replaced by an equivalent circuit consisting of a current source I n in parallel with the resistance R n, where I n is the short circuit current through the terminals across which you are finding Thevenin, and R n is the input resistance at the terminal when the independent sources are turned off. So, why we are using the Norton theorem? It simplifies the network in terms of current instead of voltage. it reduces the network to simple parallel circuit with the current sources and a resistor. And just like you look into when there is an analogy between Norton theorem and Thevenin theorem. So, here we have a network like having a linear two terminal circuit across AB, a Norton circuit. It can be modified to as a Norton equivalent, where we have a Norton equivalent current I1 as a IN as a current source in parallel resistance RN and across the AB. So, this is of course, we are converting to equivalent to a current source with the your resistance in parallel to this. So, kind of parallel circuit also. Now, coming to step to determine the normal Norton equivalent resistance and the current IN, the Thevenin and Norton resistance are equal. So, RN equal to RTH. So, RN is calculated in the same way as the RTH, and to find out the Norton current IN, determine the short circuit current flowing through the terminal AB, and this short circuit current is the Norton equivalent current IN, and that is IN equal to ISC, the short circuit current across the terminal like. So, close relationship between Norton and theorem, we can call it RN equal to RTH and IN equal to VTH upon RTH. So, since VTH and IN and RTH are related, to determine the Thevenin or Norton equivalent circuit requires to open circuit voltage VOC across the terminal AB, the short circuit current ISC at the terminal AB, and the equivalent or input resistance RIN at the terminal AB when all independent sources are turned off. So, coming to an example to find the Norton equivalent between the terminal A and B, considering the case without dependent sources. So, we have here a current source, a voltage source, and the three resistances in this network across the terminal AB. So, according to the definition, to find out, typically finding RN or RTH replacing on independent voltage and current sources as short and open circuit. So, we have typically open circuit the voltage source and remove the current source. So, this is the network, these three resistance comes in series with in parallel of 5 ohm. So, we are finding out this RN in this network is only 4 ohm, and that is equivalent to RTH also. Now, finding out the IN, the current when these terminals are short circuited. So, for IN short circuit the terminal AB in figure and ignore the 5 ohm resistance because it has short circuited. So, this resistance has no value when you have short circuited, because most of the current will flow through it. So, now in loop 1 we can find out the current is already 2 ampere, and in loop 2 we can find out typically the current is minus 20, you can call it 20 I2 plus minus 4 I1 because of this, and minus 12 because of this voltage source, and on solving these two equations we get I2 equal to 1 ampere equal to ISC equal to IN, and now this Thevenin Norton equivalent to is 1 ampere current source with the 4 ohm as a Norton equivalent resistance. That is a Norton equivalent circuit of this network like. So, another example to find out the Norton equivalent between terminal A and B of this network with the dependent sources, because here you can call it this source current Ix is here, and this is the current source which is dependent on this. So, here you have a Ix current, here 2 Ix current is flowing in parallel to the typically 5 ohm resistance like. Now, finding out the typically RN, you can call it Norton equivalent resistance. So, set the independent sources equal to 0, that voltage source, and connect a voltage 1 volt source here to the terminal and ignore the 4 ohm resistance, because it is already resistor because it is short circuited, and also due to the short circuit the 5 ohm resistor, I mean the voltage source, the dependent current source, and hence the Ix equal to 0. So, at the node A, I0 will be 1 upon 5, that is 0.2 ampere, and Rn will be V0 I0, that is 1 volt divided by 0.2 ampere will be 5 ohm, that is IN. And for now finding out the IN, that is short circuit current. So, short circuit terminal at AB and find the current ISC at the indicated here. So, 4 ohm resistance, the 10 volt typically voltage source, the 5 ohm resistance, dependent current source at all parallel, hence Ix will be here, will be 10 by 4, and that will be 2.5 ampere. So, ISC will be this 10 by 5 plus 2 Ix, this current flowing and this current. So, that will be your 2 plus 2 into 2.5, 7 ampere. So, IN is your 7 ampere, and that is your Thevenin Norton equivalent 7 ampere with your parallel resistance of what we have find out here 5 ampere like. So, now coming to another theorem that we call it maximum power transfer theorem, that use typically examples where it is used. The application is like a solar PV, which is coming a big way. I mean like when we really feed this solar power typically with the maximum power theorem with the charge controller into the battery, and then we of course feed it to inverter from the battery and to convert AC power. So, it is very coming applications, and you can call it the volt ampere characteristic or VI characteristic of PV is your this kind of nonlinear relation, and here we have to apply, we want to get a maximum power from this PV panel on this characteristic. So, that is neither on, you can call it the maximum voltage nor on maximum current, it lies somewhere where it has a maximum power on this point. So, there we apply the maximum power theorem. So, it means we have to force to create a equivalent impedance or resistance in series with the your PV, so that we can extract the maximum power. Here operating point is here for maximum power, and that is virtually it is shown that here on A point you are just have a voltage higher 39 volt, but your current is 5 ampere. So, typically it is drawing only 195 watt, and when you are operating here even on high current of 8 ampere, your voltage is already 14 volt. So, you are extracting only 112 watt, but here on this with the 32 volt and 7 ampere you are able to extract 224 watts as a maximum power. So, virtually this give you concept of maximum power extraction from the PV panel, and this is coming as a typical as a good example. So, we have to force by this charge controller, or we can call it maximum power tracker as a by power converter, some kind of circuit converter properly, so that we extract maximum power from the typically from the solar panel. Similar example is its application in communication system, and we have to put the maximum power typically from the transmitter towards the receiver antennas, and typically applying for different communication application for typically coaxial cable network or fiber network. I mean the maximum power transfer from typically from one side network to the typically for different devices for communicating the signal. Like the other example is typically stereo amplifier design, where we have to do impedance matching with the typically here in the amplifier or in the speaker. And well, for this further applications is auto amplifier, where we are going to match, I mean we have a here internal resistance that you can call the Thevenin equivalent, I mean with the voltage source, and here we have a typically you have a speaker resistance that is RS. So, we have to have a like a maximum power transfer from this source to this. So, we have to modify this internal resistance in such a manner that maximum power goes to the your amplifier like, and that relation goes to that you must have a V out equal to V s into R s upon R s plus R I. So, accordingly you have to change this R I, so that the maximum power that is equal to V out is square divided by R s is the power which is going to the speaker like to amplify it. So, accordingly you have to modify the parameter of this circuit of this amplifier like, or you have to do impedance matching which give a maximum power output, and that we have to do with the amplifier internal impedance, adjusting this value from here like also by power design. So, many applications of circuit require the maximum power available from a source to be transferred to a load resistor RL, and statement is the maximum power is transferred to the load when the load resistance equal to the Thevenin resistance as seen from the load, that is RL equal to RTH as shown in the figure here. So, you have a voltage source VTH, you have RTH, we already got the Thevenin equivalent of that we can represent a very complex network equivalent to Thevenin voltage and Thevenin typically resistance, and then we have a load resistance. So, if load resistance is changed in such a manner that equivalent to Thevenin resistance, then only you will be able to transfer the maximum. So, this is the variation of RL, when it is equivalent to a Thevenin voltage, then only the maximum power is transferred to the load. So, by varying the load resistance, the power delivered to the load varies as shown in the figure here like. So, the derivation of this in this network, we can say the value, why we have taken a very simplified network, because any network can be simplified equivalent to Thevenin network. So, if the value of the load resistance is RL, then the current flow through the circuit will be I equal to VTH divided by RTH plus the RL, and now we can find out the power transfer to the load, that will be P equal to I square RL, or you can call it the VTH divided by RTH plus RL, that is the current square into RL, and that will be VTH into RL divided by RTH square plus 2 RL RTH plus RL square, and the power will be now from this. You can keep it like a typically VTH square divided by RTH. You can take divide by RL square plus 2 RTH plus RL. Now, this power, if we take a typically the power delivered to the load will be I square RL. So, it will be VTH square divided by RTH plus RL, that is the current square into RL. Now, this we can do the maximum for transferring the maximum power. We take a derivative of power with respect to the this RL resistance. So, here VTH is not a function of RL. So, this VTH square RTH is also not function. So, we only can vary the RL in this circuit. So, we take a derivative of this. So, it comes RTH plus RL square minus 2 RL RTH plus RL divided by RTH plus RL square 4, and that is you can call it V square RL plus RTH plus RL minus 2 RL divided by RTH plus RL cube equal to 0. So, taking this like a numerator equal to 0. So, we get 0 equal to RTH plus RL minus 2 RL equal to RTH equal to RL equal to 0. So, we get the RL equal to RTH. So, this give you from solving for maximum power, they are taking a derivative of the power with respect to RL, because RL is the only variable we can think about. So, power transfer from the source to the load is a maximum when resistance of the load is equal to the internal resistance of the source, and this condition referred as a resistance matching, or let us say in case of AC in general we call it the impedance matching. So, maximum power conditions is the maximum power transferred to the is obtained equal to PTH equal to VTH, is Thevenin voltage square divided by 4 RTH, and the total power delivered by the source will be P equal to IL square into RL plus RTH, that will be equal to 2 into IL square RL. The efficiency of maximum power transfer condition is obtained P equal to IL square RL divided by 2 into IL square into RL equal into 100, that comes only 50%. So, we transfer only, you can call it the 50% transfer of the power from this. And this is typically what we have already shown earlier also, that how if we plot this power versus the load resistance, it comes the maximum only when load resistance equal to Thevenin resistance in this circuit. Power dissipated in the load is a function of RL like. So, just an example, example 1, find the value of the adjustable resistance R, which results in a maximum power transfer across the terminal AB of the circuit shown in this figure. So, we have a 100 volt source with the 3 resistances of 10 ohm to 15 ohm and 5 ohm with the RL. So, we can take a Thevenin equivalent of this across AB terminal. So, when we take a Thevenin equivalent, we just make a open circuit of that. So, we have a VTH equal to VAB equal to typically V15, because there is no current flow here. So, it will be I15 into 15. So, I15 will be here typically 100 divided by this total resistance of circuit 10 plus 15, that equal to 4 ampere, and VTH will be 4 ampere into 15 volt, that is a 60 volt. So, and the Thevenin resistance will be when we just typically remove the voltage source and see the open circuit impedance here. So, that is a 10 ohm is in parallel with the 15 plus 5 ohm, and it becomes equal to 11 ohm. So, Thevenin equivalent of this circuit is with the 60 volt with the 11 ohm resistance in series. So, that is this circuit get converted finally to 60 volt source here, that is open circuit voltage across the terminal, and 11 ohm resistance is in series, that is the Thevenin equivalent. And now, we have RL here. So, maximum power transfer will be only when this load resistance is equal to the Thevenin resistance, that is 11 ohm, and the power delivered to the load will be your I square RL. So, power current will be VTH divided by the total resistance of this circuit RTH, which RL square into RL, and that is VTH squared by, because both are equal. So, it will be your, you can call it like a 4, because 2 will be squared to 4th, and this will be equal to RL will cancel out. So, this will become 60 square divided by 4 into 11. So, it becomes your typically 81.82 watt. Now, application is as we already talked about communication and electronic circuits, where the source usually has a relatively high resistance and where it is desired to transfer the largest amount of power from the source to load. Now, coming to some of the theoretical problems. What is the superposition theorem? Answer is in any linear network containing 2 or more independent sources, voltage and current sources, or combination of voltage and current sources, the resultant current or voltage in any branch is the algebraic sum of the current and voltage caused by each independent sources acting along with all other independent sources being replaced meanwhile by their respective internal resistances. And what is the limitations of superposition theorem? There are three main limitations we discussed: not used in power calculation, not used in nonlinear circuit, and not used in for typically complex circuit. What should we should do for making the voltage source 0 in superposition theorem? You have to short circuit the voltage source. What we will do with making the current source 0 in superposition theorem? You have to open circuit the current source. What is the Thevenin equivalent voltage? Open circuit voltage from the load side, terminal voltage is the Thevenin voltage. Can we use the Thevenin theorem in a circuit containing BJT? Answer is no, we cannot use the Thevenin theorem is only for linear circuit. BJT is a non-linear network element, and hence we cannot apply the Thevenin theorem where in the circuit we have a BJT. What is the Thevenin theorem? In parallel circuit, Thevenin theorem states that linear two-terminal circuit can be replaced by an equivalent circuit consisting of voltage source VTH in series with the resistance RTH, where the VTH is the open circuit voltage at the terminal and the RTH is the input or equivalent resistance at the terminal when the independent sources are turned off. The Norton resistance is found by the ideal current source having infinite internal resistance. Hence, we have like an open circuit where the ideal voltage sources have 0 and internal resistance. Hence, we behave as a short circuit. So, to obtain Norton resistance, all the voltage sources are shorted and all the current sources are open. Question 9: what is the following is the known as dual of Norton theorem? The Thevenin theorem is considered the dual of your Norton theorem. What is the relationship in Thevenin equivalent and Norton equivalent circuit? This Thevenin Norton equivalent resistance is equal to Thevenin equivalent resistance, and the Norton equivalent current is the VTH upon RTH. So, what is the efficiency at the time of maximum power transfer to the load? Is a 50%, because we have a both internal resistance equal to Thevenin equivalent resistance or equivalent resistance equal to the load resistance, only then maximum power transferred. So, efficiency is 50%. Now, coming to solved problems, use the superposition theorem to find out in the circuit shown here. We have a circuit where we have a 6 volt independent voltage source with another current source in parallel with the 4 ohm and 8 ohm resistance. So, solution is here two sources, let the V equal to V1 plus V2. So, where V1, V2 are the contribution due to the 6 volt source and the current 3 ampere current source respectively. To obtain V1, then set the current source to 0 as shown in the figure A. So, this is typically where the current source is removed. So, we can find out from this loop, typically 12 I1, because total current with the across the through the 12 ohm resistance minus 6 equal to 0. So, I1 is equal to 0.5 ampere and V1 will be typically here 4 into I1, that is 2 volt, and we may also use the voltage division to get V1 by writing even V1 equal to 4 upon divided 4 plus 8 equal to 6, that is 2 volt. To get the V2, set the voltage source to 0, and we have a circuit figure 1b here. So, where voltage source is shorted. So, we can find out now typically I3 will be equal to here 8 into divided by 4 plus 8 into 6, that is 2 ampere, the current flowing through here, and V2 will be 4 into I3, that is 8 volt. So, we can find out now total V equal to V1 plus V2, that is 2 plus 8 volt and 10 volt, like that is virtually superposition apply. Now, coming to the second numerical example, find I0 in the circuit of figure shown here using the superposition theorem. The current we have to find out in this here, we have a typically one voltage independent source, one voltage dependent source which depends on current, and the one current source. So, now circuit involved a dependent source which must be left intact. So, we left it I0 equal to I0 dash plus I2 dash, I0 dash double dash. So, where I0 dash plus I0 double dash are due to the 4 ampere current source and 20 ampere voltage source respectively. To obtain I0 dash, we first turn off the 20 volt source. So, that we have a circuit shown here figure 1a. So, applying the mesh analysis in this circuit, because here typically we remove that voltage source. So, here I1 will be typically the 4 ampere which is current shown here, and we can find out for the loop 2 minus 3 I1, that is typically current here, plus 6 I2, that is the current typically in the total resistance I2, minus I 1 here minus the typically this voltage source equal to minus 5 I dash equal to 0. For loop 3, on this loop we can find out 5 I 1 minus 1 I 2 typically here plus 10 I 3 the total one and plus 5 I 0 dash. So, that is and but at node 0 here we can apply the KCL. So, I 3 will be equal to, because that is the current typically coming in and equal to the current I 1 minus I 0. So, that give you equal to 4 minus I 0 dash. From this substituting equation 2 and 5 and 3 into 4 gives the simultaneous equation 3 I 2 minus 2 I dash equal to 8 and I 2 minus 5 I 0 dash equal to 20. So, we can solve these two equations to get value of I 0. So, I 0 comes from here typically 52 by 17 ampere, that is typically I dash. Now, we go to the typically to obtain the I double dash, where we can turn off the 4 ampere current source and so that circuit becomes loop and keep the voltage source. So, now in this first loop loop 4, in this case we can write 6 I 4 minus I 5 equal to minus I 5 I double dash equal to 0, and loop 5 this here we keep minus I 4 plus 10 I 5 minus 20, that voltage source plus I 5 I 2 dash equal to 0. So, but now I 5 equal to minus I 0 double dash. So, putting this I mean 9 into 10 we can get 6 I 4 minus 4 I 2 dash equal to 0 and I 4 plus I 5 I 4 double dash equal to minus 20. Solving this we get I 0 double dash equal to minus 60 upon 17. Now, substituting this two equations, two value I 0 will be minus 8 upon 17, that is minus 0.4706 ampere, and that is virtually you can call it like a equivalent to the total current flowing into the that what we are interested in original network. Now, coming to the another example of superposition theorem for the circuit shown here. Use the superposition theorem to find out current in the 3 ohm resistance, calculate the power delivered to the 3 ohm resistor. So, to find out there are 3 sources, I mean like 2 voltage independent sources and 1 current source. So, we have to find out the current into this. I will be equal to the current by the all 3 sources I 1 plus I 2 plus I 3. Now, coming to circuit one by one. So, where we take a first voltage source, so consider 20 volt source only and short circuit 16 volt and open circuit 2 ampere source. So, circuit becomes quite simplified. You have these two sets resistance in series with this. So, that is total resistance comes of 2 ohm 4 ohm of considering, and the total current going through typically here in this from this circuit is like 20 divided by this resistance, and now we can find out the current typically going to 3 ohm, that current 2.5 by current division. Now, coming to consider only 2 ampere source and only short circuit to only take a current source and short circuiting the voltage sources typically of 20. So, it circuit comes in this fashion, which you can convert this equivalent into this manner, and from which you can find out I equivalent in this circuit, R equivalent of the total resistance of these two parallel and then series with this, that comes 5.33, and now you can find out the current I t equal to 2 divided by 5.33. This is I 2 here what we got it equivalent to I t that is 0.375 ampere. Now, consider the third source, that is 16 volt source and short circuit 20 ampere, open circuit that current source. So, you get R equivalent in this circuit equal to that 5.33 ohm, and you can find out I t here, that is 3 ampere, and I 3 typically minus I 3 is equivalent to that 1 ampere. So, I 3 is minus 1 ampere current flowing into the typically in your 3 ohm resistance. Now, total current will be I 1 plus I 2 plus I 3 flowing into 3 ampere. So, that all 3 current we got it. So, it become 1.875, and now power deliver in this will be I square R. So, you can find out this 1.875 square into 3, that is a 10.546 watt, that is P 3 3 ohm. Now, coming to now another example, question 4, example 4 of the Thevenin theorem. Find the Thevenin equivalent circuit of the circuit shown here to the left of the Thevenin terminals across A B. Then find out the current through 6 if this is 6 ohm and 36 ohm. So, we have to find out first Thevenin equivalent of this circuit. Coming to equivalent to this here, to find out Thevenin resistance, we have to open circuit the current source and short circuit the voltage source to find typically RTH turning off the 32 volt voltage independent voltage source, replacing it as a short circuit, and the 2 ampere current source as a replacing the open circuit. This circuit becomes in this manner. So, 2 resistance in parallel with one series, that become RTH equal to 4 ohm, and the second step is to find TH, volt TH applying the mesh analysis to 2 loops here replace as shown here. So, that you apply I1, that is minus 32 because it is entering with the negative terminal, plus 4 I1 plus 12 I1 minus I2, that equal to 0. So, and second loop is just like your current I2 equal to minus 2 ampere. So, solving this you will get a putting I1 value here. So, you get I1 equal to your 0.5 ampere and VTH equal to your typically here is a 12 into I1 minus I2. So, that becomes 12 in 0.5 plus 2. So, that becomes 30 volt. So, that becomes typically your Thevenin equivalent here is the 30 volt with 4 ohm resistance in series, and now we have a load here. So, that is the your load current will be VTH upon RTH upon plus RL. So, when RL is equal to 6 ohm, you have IL equal to 30 divided by 4 plus IL. So, putting value of 6 ohm of RL, that become 30 upon 10. So, this is 3 ampere, and when RL equal to 36, you put the RL equal to here 36. So, it becomes 30 by 40, it becomes 0.75 ampere. So, Thevenin equivalent circuit shown here, and these are the two current here like. Now, coming to another example of this 5, find the Thevenin equivalent of the circuit shown here terminal. We have a one current source, that is typically dependent current source of Ix current here. So, now we can find out the RTH. So, there are no dependent source here. So, we have to excite the circuit by external 1 ampere current source and replace the current typically circuit to shown here. So, I0 equal to here 1 ampere. Now, from here we can find out typically from nodal analysis at terminal A, so 2x 2ix, this is the current source, minus V0 minus 0 divided by 4 the current flowing here, then V0 minus 0 divided by current flowing into this and equal to this current source plus minus 1. So, you get the Ix equal to 0 minus V0 divided by 2, that becomes minus V0 by 2, that is the Ix, and substituting 2 into 1, we get the 2 into minus V0 by 2 plus V0 minus 4 by 4, V0 minus 4 by 2 minus 1. So, V0 we get the minus 4 volt, and now we get the VTH RTH equal to V0 upon I0. So, that is minus 4 divided by 4, that is minus 4 ohm. So, negative value of the resistance tells that according to the passive sign convention, the circuit is supplying power, and resistance cannot supply the power as it is the passive source. So, in this circuit dependent voltage source supply the power, and this example shows that how a dependent source and resistance could be used as a similar to the negative resistance like. Now, coming to step 2, finding the VTH. So, since we do not have any dependent voltage source in this circuit, so value of the Thevenin equivalent voltage will be 0, and this is typical. Now, coming another example, find the Thevenin equivalent of a circuit across the terminal here. So, we have a one independent voltage source and one with dependent voltage source here of this voltage typically. So, finding out the VTH, to obtain the VTH, applying the KVL to the loop here. So, minus 70 volt plus 10 plus 20 into I, the current flowing into this network, plus 4 I0 this voltage source equal to 0. So, V0 equal to 10 K I, and V0 is in equation, well, if we put it here. So, that will 70 equal to 70 K I equal to I equal to 1 milliampere, and using the KVL on typically on left side. So, it will be like a 70 plus 10 K I plus VTH. So, VTH is 60 volt. So, you get the typically now finding out the RTH, remove the independent voltage source of 70 volt and apply 1 volt dependent voltage source and excite the terminal typically 1 volt here. So, V0 is your minus 1 volt, and applying the KVL in the loop right typically in this loop. So, it is your minus 1 plus 20 K I, that is the current here I1 plus 4 V0 here. So, that I1 will be equal to your 0.25 milliampere, and I2 will be I1 plus this your 1 upon 10 to power 3, because that is a, and that become 0.35 milliampere. So, therefore, RTH will be 1 volt divided by I2, 1 upon 0.35, it is kilo ohm, and that will be equal to 2.857 kilo ohm. Now, coming to example 7, solve the circuit in I in the circuit below using Thevenin equivalent theorem. So, we have a 2 independent voltage source and we have to find out typically the current here. So, coming to as a step 1, finding the Thevenin resistance, applying the theorem across 12 ohm resistance. So, remove the independent voltage source by short circuit and then reducing the circuit as shown here. So, you can find out the Thevenin equivalent of 2 equivalent volt resistances, and that comes equal to RTH equal to 8 ohm. And now, finding the VTH considering the circuit here. So, consider I equal to in a outer loop. So, you can have a minus typically 10 into I plus 150 minus 60, that is typically here. So, VTH will be your 60 volt, and now you can have a circuit here VTH equal to 60 volt and RTH equal to 8 ohm with the RL equal to 12. So, you have applying this IL equal to 60 by 12 plus 8, that is 3 ampere. Now, coming an example 8, applying the Thevenin theorem to find out VO in the circuit here. So, you have a current source, you have a voltage source, and we want to typically apply the, you can call it the Thevenin theorem to find out VO across this 10 ohm resistance. So, we have to open circuit this. So, we find out the Thevenin equivalent of 10 ohm resistor. So, finding out the RTH, remove the independent voltage source and current sources. So, by removing this, so we get this equivalent circuit. So, you have a these two resistance set of resistance in parallel with the 1 ohm. So, that comes RTH equal to across it 5 ohm, and finding out the VTH, I mean applying the nodal equations here. So, we get the typically this current equal to V 1 upon 16, that is on node 1, per V 1 minus V 2 typically by 4 equal to, now from here we get the 48 equal to 5 1 minus 4 V 2 in the V 1 V 2 this one equation, and now the node 2 we apply the equation V 1 minus V 2 divided by 4 plus typically 12 minus V 2 this voltage by 5, and that will equal to 0. So, this give you 48 equal to minus 5 1 plus 9 V 2, and also solving 1 V 1. So, we get the VTH equal to V 2, that is 19.2 volt, and therefore, V 0 will be, I mean typically the voltage here will be your 10 by 10 plus 5 into 9 point, so 12.8. So, this comes your typically a Thevenin equivalent of getting from 19.2 volt and 5 ohm resistance of equivalent to this, and you can apply 10 ohm now load across it, and this is the typically the output voltage across the load. Now, coming example 9, find the Thevenin and Norton equivalent at the terminal of A B. So, you have a 2 current sources and voltage 1 voltage source. So, we have to find out now Thevenin resistance. So, we have to remove the current, typically the current sources, and short circuit the voltage source, and this we get the RTH here, just addition of these parallel with this. So, we get the RTH by calculation equal to 4 ohm, that is a Norton equivalent resistance also, and finding out the open circuit voltage here. So, we have this typical circuit for getting Thevenin voltage. So, applying the voltage transformation to the 1 ampere current source here typically. So, here we get the typically 14 plus 6 these 2 voltage source minus VTH, here the VTH divided by 14.6 equal to 3 plus VTH by 5, the current flowing through this. So, VTH it comes minus 8 volt, and now we get the here you have voltage source of 8 volt with the 4 ohm resistance. So, you can get I source typically the Norton current of VTH by RTH minus 8 by 4. So, I n equal to minus 2 ampere here in the direction. So, this is your Thevenin, this is equivalent. So, where the you can RTH equal to R n equal to 4 ohm and VTH minus 8 volt and I n equal to minus 2 ampere. So, these are the Norton Thevenin equivalent and Norton equivalent of the circuit which we have solved like. Now, coming to typical example of maximum power theorem, find the value of RL for the maximum power transfer in the circuit of figure and find the maximum power transfer. So, this we have to find out what is for if we transfer the maximum power here. So, we have to find out again the Thevenin equivalent of it. So, to simplify it, to calculation of Thevenin voltage and Thevenin resistance of terminal across A B by removing this RL. So, find the TH, to remove the short circuit the current voltage source and open circuit the this. So, this circuit can just become equivalent to this. So, you have a 2 resistance in parallel and 2 in series, this RTH becomes 9 ohm, and now applying the for getting VTH. So, applying the just keeping open circuit. So, you get the VTH by solving the equation of these two. So, minus 12 volt plus 18 total resistance of 18 I 1 minus 12 I 2. So, this give you I 2 equal to minus 2 ampere and solving I 1 minus 6.8 ohm. So, applying KVL for getting the VTH. So, minus 12 plus 6 I 1 plus 3 2 plus VTH. So, VTH comes 22 volt. Here, and for maximum power RL equal to RTH equal to 9 ohm, and then power transfer will be your VTH upon 4 RL 22 square into 4 into 9, that becomes 13.44 watt. Now, coming to another example of maximum power theorem transfer, find the value of RL for maximum power transfer to the circuit. So, here it is a RL and we have a 2 voltage source with the 3 resistance. So, we have to again find out the Thevenin equivalent. So, Thevenin equivalent voltage typically to find out by the nodal here. So, voltage we want to find out V minus 20, typically this by 5 the current flowing through here, and V by directly 20 here to find out this equal to 0. So, from which we get the V equal to 16, and now we can find out the V 16 volt and applying the Kirchhoff. So, in this circuit, so we get the 16 minus 12 minus VTH equal to 0. So, VTH is the 4 volt to get here the open circuit voltage, and resistance is simply that we typically short circuit the voltage source. So, it comes this circuit. So, RTH is 12 ohm. So, now this circuit modified to 4 volt Thevenin equivalent voltage with the 12 ohm Thevenin equivalent resistance, and RL is here. So, now from this we can find out what will the typically the power flow here as a maximum power. This will be equal to this. So, maximum power will be only when RL equal to 12, and we can find out power maximum equal to I square RL. Keeping the value here, we get the 0.33 watt. Now, there are some unsolved problems. I mean, one you can exercise the typical problems of unsolved problems also, like so on the basis of what we have talked about, like for all 4 theorems, and these are the of course references for this topic today, and thank you very much.